Welcome to our first of two videos on building and training a convolutional neural network on the CIFAR 10 dataset. Now that we're familiar with all the main building blocks, we can get to work and start putting them together. First, I'll provide a brief overview of the CIFAR 10 dataset so that we understand the task to be solved. Then in preparation of model building, we'll learn how to use TensorFlow's new estimator and dataset utilities. We'll conclude this video, part 1, by implementing the input pipeline for our model using the tf.data API. The CIFAR 10 dataset is one of the most popular public datasets for image recognition tasks. It consists of 60,000 images, each labeled by one of 10 possible classes, listed here on the left of the picture in the slide. And we will use 50,000 labeled examples for our training set and 10,000 for our evaluation set. As usual for the task of image recognition, our model's goal is to learn how to accurately predict the class of a given image, such that it achieves high accuracy not only on the training and evaluation sets, but ideally on any unlabeled image we may ask it to label in the future. So before coding up a model, it's useful to have a high-level understanding of what you're about to build. Let's sketch our model diagram. Here is a common layer sequence seen in convolutional neural networks. The output of a convolutional layer is fed to the batch normalization operation, and then max pooling. Note that the convolutional layer often uses the ReLU, short for rectified linear unit, as its activation function. Some people prefer applying the ReLU function after the batch norm layer rather than before it, and that's how we will actually implement it too, as was specified in the original paper of batch normalization. We will call this layer sequence of conv2d to batch norm to max pool as simply conv block to simplify our illustration. Our model will begin with two such conv blocks, followed by two fully connected or dense layers with ReLU activation functions, and the last layer will be a fully connected layer with softmax activation function, which will output the probability of the input image being in each of the 10 classes in the CIFAR 10 dataset. After some pre-processing, we'll feed in batches of images, here a batch of size 1, and output the predicted labels for the batch. For this example, the correct label for our single example batch is automobile. Note that this 32 by 32 image is actually one of the images in the CIFAR 10 dataset, and its label is indeed automobile. TensorFlow recently released the tf.estimator module for greatly simplifying the process of creating, training, evaluating, saving, and restoring models. In addition, it also released the tf.data API for simplifying the process of building a proper input pipeline, which used to be a very tedious task. Let's first see the basics expected with tf.estimator, and we'll see how to work with tf.data during the input pipeline coding process. After reading through a handful of tutorials in the documentation for tf.estimator, I placed the main information needed to know in this template-like file. First and foremost, when writing a custom estimator, we need to define the model function, with arguments as shown here. I encourage you to pause and read through the docstring here, but the high-level summary is that, given a batch of labeled inputs, features, labels, we build our model's graph and training nodes. This is where we'll be defining our neural network's layers, loss function, and training operations. We are expected to place certain variables like the model's trainop in a tf.estimator.estimator spec and return it. This is one example of what that might look like. So you just return an instantiated estimator spec, and depending on which mode you're in, again, I encourage you to read the docstring, that will determine what you pass as inputs to this estimator spec. This begs the question, okay, but where are these labeled batches coming from? Great question. That's where the input function comes in. And notice that the naming conventions I'm using here are indeed what's expected. Whenever we call our estimator's train, predict, or evaluation methods, we must pass an input function as a required argument. We are free to choose whatever parameters we'd like for this function, and the reason for that will become clear when we start using it. We are, however, required to return the input batch and labels batch that will then be sent as the first two arguments to our model function. See here, we returns a features and labels, and these are the same ones that are fed as input to the model function. Again, I encourage you to spend some time reading this template file. It contains information from a few key resources that I'll also provide in the additional resources slide, but here are all the key information is combined into a single template. Now, time to start filling in these blanks for our model. We'll begin by implementing our input function. I'd suggest first just watching the video to get a general feel for the process, and then try coding it up yourself. I often find that I remember a lot more from tutorials if I manually type out the code myself, since it forces me to read each and every character of every line. As mentioned, we are free to specify which parameters we would like to be passed to our input function. Here I've chosen the directory of the data for CIFAR 10, as well as the batch size. The source of the data will be downloaded to your directory when you run the file for the first time. We start by retrieving a list of strings that give us the path to all the data files. I'm using a handy utility that I like to use called glob. So I can just specify that I want to start at the data directory, subdirectory CIFAR10 batches bin, and I want to get a list of all files that match data batch and then anything else after that, and then .bin. You are free to use whatever utility you like to get the file names, but glob makes this, as you can see, pretty straightforward. Datasets come in many different formats, and part of machine learning is getting comfortable with a variety of them. Here our files are binary records where each record is a fixed number of bytes and contains a label image pair. We will be using the tf.data.fixedLength record dataset to make consuming this type of data simple. It expects a list of file names, which we've already gotten, and the number of bytes each record takes up. At this point, if we just stopped at this line here, our dataset would just spit out sequences of bytes instead of formatted image label pairs. That's why we have to call dataset.map on our decode line function. This returns a new dataset object that will transform each binary record as specified by our decode line function, which accepts a single binary record as input, which I've called value, and outputs the desired transformed version. For us, we want to convert the binary record into an image tensor and its corresponding label. So let's see how this decode line function works. So first, we convert each byte into its 8-bit integer representation and extract the label as the first integer in the list. This is just how the CIFAR10 dataset is formatted, and all the details can be found in the links in the additional resources slide, for any viewers with a passion for data formats. We continue by extracting the remaining chunk into what will become our image tensor. After some reshaping so that the dimensions represent the height, width, and depth, which is the number of channels, 3 for RGB, notice the last few function calls. We see some of the image pre-processing we discussed in the previous videos. We apply some random distortions and standardize the image, returning the desired image label pair. Float image, label. Okay, so we're done, right? Nope. So far, we've just decoded each line of our data into pre-processed image label pairs. We still need to do things like shuffling and batching before it's ready to be fed to our models. Users that have waded through the journey of building an input pipeline in early versions of TensorFlow might stand in disbelief when seeing how simple it has become. The handful of lines code you see here would have easily taken me 100 lines or more in TensorFlow just a year ago. That's a really beautiful thing we have here. We can directly call dataset.shuffle to customize the shuffling process in our input pipeline. We then pass our batch size to dataset.batch, and voila, we are nearly done. The next few lines are the most common way of finishing this up. We instantiate a dataset iterator that will iterate over our batches, returning image batch image label pairs. Now to actually access the TensorFlow operation that retrieves the sequence of batches, we call getNext as shown. I've also chosen to explicitly set the shapes of our images and data, which serves to fill in any nuns in this shape, something I've been observing has been popping up for the batch dimension, even though we've already told TensorFlow that batch size is this passed in number right here. So I anticipate that this won't be necessary very soon once the API gets a little more updated and settled in. So that's it, our input function is complete and we are now ready to return image batches with their labels. As always, make sure to read through the links here for an in-depth look at the topics covered today. Stay tuned for part 2 of our model building journey, where we will implement our model function and show how to train and evaluate its performance on the CIFAR10 dataset. See you next time!